Hi Bobcats. In this video, we're going to take a look at how you calculate the equilibrium constant for a conjugate acid-base pair. Usually when you go to look at the tables, only one of the chemicals from a pair will be listed. And so we'll see here how you get the equilibrium constant for the other half. Our big overarching objective here is to be able to calculate the pH of salt solutions. One of the pieces that we will need in order to do that is to be able to find the Ka or Kb for the conjugate pair of a weak acid or weak base. So there's a straightforward relationship between Ka and Kb for a conjugate pair. If you take Ka times Kb, you get Kw. And since usually only one piece will be listed in a table of Ka or Kb values, you'll use this equation to figure out what the other one is. So to give you something concrete here, you may be working a problem where you need Kb for the fluoride ion. But you go look at a Kb table and fluoride's nowhere to be seen. However, Kb is the conjugate base of the weak acid HF, hydrofluoric acid. And so you can use the number that you can find in a Ka table for HF along with this equation to calculate what Kb is for the fluoride ion. So let's look at an example of this sort of calculation. Let's find the value of Kb for the acetate ion, given that Ka for acetic acid is 1.8 times 10 to the minus 5. So acetic acid is HC2H3O2, and acetate is C2H3O2 with a minus 1. So they are a conjugate pair. So we can use the equation that Ka times Kb is equal to Kw. Now the Kb that works in this equation is the Kb for acetate, and the Ka that works in this equation is the Ka for acetic acid. Since Kb is the thing we want to find, I'm going to go ahead and rearrange this equation, and that gives us that Kb is Kw divided by Ka. Kw is 1 times 10 to the negative 14, and Ka is 1.8 times 10 to the negative 5. I'm going to run that through my calculator. 1 EE negative 14 divided by 1.8 EE negative 5. And that's going to give us 5.6 times 10 to the negative 10. So that is equal to Kb for the fluoride ion. Fluoride was the previous example. That is Kb for the acetate ion. In this example, we're asked to determine which one of these anions has the largest Kb value. These are all the conjugate bases of weak acids. NO2 minus 1 corresponds to nitrous acid. PO4 minus 3 corresponds to the hydrogen phosphate ion. And N3 minus 1 corresponds to hydrozoic acid. Now, we could use the equation that says Kb is equal to Kw divided by Ka, just like we did in the last example. I'm going to go ahead and crank these numbers through my calculator, and we'll add them here because I want to prove to you that a different way of working this problem gets you the right answer without as much work. So let's go ahead and run all of this through for the, and here I guess list which anion we're working with here as well. So for the nitrite ion, and then the phosphate ion, and finally for the azide ion. Okay, so for nitrate, I'm going to take 1 times 10 to the negative 14 and divide it by 5.6 times 10 to the negative 4, and that's going to give me 1.8 times 10 to the negative 11. For the phosphate ion, I'm going to want to use the third ionization constant because that's the one that will yield phosphate. So I'll have 1 times 10 to the negative 14 divided by 4.8 times 10 to the negative 13, and that's going to give me 0.02, or if I did that in scientific notation, that's going to be 2.1 times 10 to the negative 2. And then for our last one, 1 times 10 to the negative 14 divided by 2.5 times 10 to the negative 5. That's going to give me 4.0 times 10 to the negative 10. Okay, we're looking for which of these has the largest Kb. So the largest of these values is for the phosphate ion with the 2.1 times 10 to the negative 2. However, we could have gotten there by looking just at the Ka values and recognizing that there's an inverse relationship specified by this equation at the top of the page. If Kb is big, Ka has to be small. If Kb is small, Ka has to be big. So Kb and Ka are inversely proportional to each other. So once we know the values for Ka, if we want the smallest Kb, we look for the biggest Ka. If we want the biggest Kb, we look for the smallest Ka. So we could just simply compare these three Kas, 5.6 times 10 to the minus 4, 4.8 times 10 to the minus 13, and 2.5 times 10 to the minus 5. The smallest of these was for the phosphate ion, or was for the hydrogen phosphate acid. And so that means correspondingly the biggest Kb would be for that one. Our objective was to calculate the pH of salt solutions. Being able to figure out the relationship between Ka and Kb for a conjugate pair is the first step in being able to do this calculation.